Log on, tune in, find out. Another good idea from Cambridge.
That means Doran from Zurich. He's speaking on geometric invariant theory.
So is the microphone working? I hope so. All right, so I'd like to thank the organizers for the invitation, and I have to say it looks like it's shaping up to be a great workshop, and I'm sure a program thereafter. So again, thank you. I've been asked to speak on geometric invariant theory, or GIT, and there's sort of several obstacles to overcome, given this is 4 lectures. The first obstacle is that, at least in the British English vernacular, Git is not exactly a term of endearment. So, zeroth. I hope to convince the young people in the audience that, sure, the theory may be a little bit old and fusty, but it's also at the same time charming and useful, and happily very much alive and well. All right, the second is that because this is an old subject, we have the good fortune that there are many books on the subject, and so in a sense that means that doing too much introductory material would be redundant. For the purposes of the young, again, let me mention a couple books. There's of course the classic by Newstead. There's a very nice book by Dolgochev from about 7 years ago, Cambridge University Press, on invariant theory. And Mukai, his Japanese texts have been translated into English. They're also a good source. And of course, so these are highly readable. And there's another very good book, of course, the core text, Mumford, Fogarty, Kirwan, which although very good, I would not say is necessarily very readable. So, all right, and the second, or third, depending how you count, issue is that because it's an old subject, it's had time to grow in many different directions. And so the subject today is quite large. It's much bigger than before. And in particular, you could think, there have been many new tools, many new areas of application, and it's perhaps best to think of it more as a subset of the theory of algebraic transformation groups. So you have to be selective in what we cover. And as I said, new tools and new applications. Sort of an amusing new application, for instance, that some people seem quite excited about, can be thought of as an application to computational complexity. I may mention 1 or 2 small things about that later. And this is something that even, of course, people in computer science, but particularly in physics, are interested in. So there's a professor in ETH in the physics department who's a quantum computation theorist, and he seems very, very excited about these potential applications there. Whether or not that goes anywhere is another question. All right, but with these constraints in mind, and the idea that I want to try to do something a little bit different therefore than was covered in a text, not just a survey of the field, because it's a bit too broad, try and break down the talks roughly into these sections. Talk 1, okay, again with the aim of explaining to the young people that what's going on. People haven't necessarily studied the subject, so what is GIT, and where did it come from? So it's a subject with extremely deep roots in the history of algebraic geometry, and it's important, I think, to appreciate that, to really understand it. So by necessity, this talk is going to be somewhat historical. Talk 2 will answer more of these W questions. We had what and where. Well, how about why does GIT work? So I can, give lots of detailed proofs about certain theorem statements, but in the end, there's really only a couple of reasons why GIT works so well. And also, how is it typically used? For instance, in modular problems. The third talk and the fourth talk then be a little bit more flexible in the subject. We'll see how timing works. But the third talk you might think of as refinements of the theory because of all the structure that's present, some applications to certain moduli questions, and interesting cohomological features and developments. And the fourth talk then, sort of beyond moduli applications, there's many other ways you can use GIT, but let's just say sort of variations and applications. Okay, now of course for this workshop, it's a workshop on moduli spaces, and in the background of GIT, right from its very modern beginning with Mumford, is the idea that you want to use GIT to construct moduli spaces. So in the background, in fact, right at the very beginning of Mumford's book, we have this quote. It says, "The purpose of GIT is to study two related problems. When does an orbit space of an algebraic scheme acted on by an algebraic group exist?" So that's one. And two, to construct moduli schemes of various types of algebraic objects. The second problem appears to be, in essence, a special and highly non-trivial case of the first problem. Now, he sort of qualified his language there a bit, and I think that's wise, because as time has passed, it's clear, I think, that there were some very good early successes with GIT in describing moduli problems more or less completely. But it's certainly not sufficient in general to understand moduli problems for various reasons, and we'll discuss some of them. But it has had many successes, and when it works extremely well. So let's say that, so birationally, this statement is kind of almost trivially true. So birationally, yes, but biregularly, when it works, it gets a check plus. It's excellent. And when it doesn't, then, well, you have to do some other things, of course. So we'll discuss that a bit more later. All right. I should say one more thing. If people can't read what I'm writing because I'm writing too small or something, please shout out. And also because I've traveled many time zones, 5 times over the past 2 weeks, I'm right now high on caffeine, and so I'm relying on caffeine, and I might go too fast in some ways. Please, again, slow me down if there's an issue. All right. So schematically, what is this thing saying? It's saying that we're beginning with some classification problem. Right, maybe you want to classify linear transformations, classify varieties with some certain properties, and we hope to be able to reformulate this classification problem as a problem involving group actions. And in algebraic geometry, typically group actions on varieties. And then, with that group action, we take some form of a quotient, right? And depending how you think of the quotient, I mean, the simplest thing to do is just to parameterize all the orbits in the action on your, say, variety, and you get an orbit space. Right? As I said, this is parameterizes orbits of the action. And then, in the third leg, we go back to our original classification problem, and we want to define whatever class of spaces we're working with, moduli. Right? So there's a few remarks we have to make about this process. The first is that at each stage, we tend to lose some information. We'll see that in detail in a moment, but I'll give some schematics in a second. This issue is largely remedied, albeit at a cost, by the theory of stacks, which will be seen next week. All right. The second point I want to make is that this right-hand side of the problem somehow has a very topological, perhaps in some generalized sense, flavor. So it's really not so much a problem of algebraic geometry. The problem of algebraic geometry comes in sort of choices with the moduli and maybe an initial reformulation. It's so for instance, I mean, you can certainly do this in topology, right? We have group actions, so, and they arise all the time. I mean, you might have some vector field in the plane. This is a dynamical system giving you, with fixed points, what have you, and you think of the flows for the vector field as being one-parameter groups of diffeomorphisms, right? And you can ask, how do you parameterize these flow lines, these orbits? And you quickly come to realize that there's some obvious topological problems. So, for instance, there's clearly Hausdorffness issues. Non-separatedness issues. And perhaps the easiest way to see that, also in algebra geometric style setting, is you might have, just multiplication in the xy plane by some lambda, where lambda maybe is in, let's say, everything of the reals, whatever, or a star. So of course, you get flows like that, and you can see that this orbit, this closed orbit, is in the closure of all of these orbits, right? And so in some sense, you'd have to remove that orbit in order to separate these orbits in some sensible sense in an orbit space. So that's one issue. The second issue, as I said, is you can lose information about this action. So there's no reason to believe that the quotient space itself has retained all of the interesting information about the action, right? And there's some ways in which this is abundantly clear. So a simple example is if you consider just symmetric group actions on Cn, and you think of elementary symmetric polynomials, then we know that we get back Cn when we take a quotient. So B so for instance, we can consider Cn with a symmetric group action, permuting the variables and the map given by elementary symmetric polynomials. This is back to Cn. And so maybe if we have symmetric group actions floating around, we just look at the quotient space. We're not detecting singularities or anything there. We're just back to the same space. That could be an issue. All right, and C, there's the issue which really Mumford was interested in, which was how to stay in your category when you quotient, that quotienting stage. So for him, this was the crucial hard part, because he was very much fixed at the time on studying schemes. So in particular for Mumford, he wanted to work with schemes. They separated. That could be part of your definition. So you can do, okay. That may or may not be the right thing to do in certain cases, of course. All right. So what's an example where we begin to see some of these issues? Well, this is sort of the prototypical example of a moduli problem from linear algebra. So, right. So let's say we want to classify, so this is our classification problem, classify linear transformations. And that means up to similarity, right? So up to change of basis. And this is the standard way to get a basic moduli problem, is this goes, so the very basic idea, of course, goes back to Descartes, pick Cartesian coordinates, prove something in algebra, say, about some geometric object, and then forget that you have the algebra there. You've just said something about geometry. So more generally, we impose coordinates, we do something with those coordinates, and then remove the coordinates, quotient out by the choice of coordinates, say. So up to similarity, that is to say, change of basis. And this is something we understand very well. What happens, let's take a really simple example and see some of the phenomena at work here. So let's take our coordinates, pick our coordinates, and we'll express our linear transformation as a matrix A, n by n matrix. And similarity is just saying that this is similar, this is equivalent to this, where B is some invertible matrix, and A is going to be in our blend matrices. All right, so here we've now gone from our classification problem, reformulated using the notion of picking coordinates and then worrying about change of coordinates, to a group action question. And we want to look now at this point. Consider the orbit space and reasonable notions of quotient. Well, what happens? Let's do a really simplest possible case, n equals 2. You could do k equals c if you like. All right, so well, what happens? Well, we have our four-dimensional space. It's supposed to be four-dimensional. And we'll have some orbits of whatever dimension under GL2. So M2 by 2 decomposes into some union of GL2 orbits. And these orbits are not going to be maximal dimensional. They're not going to be the dimension of GL2. They're going to be something less. And you can easily determine that they're at most two-dimensional. But the crucial question here is, how do we parameterize the orbits? So the question is, and the basic idea, your first step might be just we want to parameterize them by using functions. So in particular, we want to separate different orbits with invariant functions. So try to separate orbits with invariant functions. Okay, so this is this is somehow the incredibly easy first thing you might do, which is basically what you do in GIT. So let's step through what happens here. So what do you mean by separating orbits with invariant functions? Well, so given two orbits, you want to find some G invariant F such that F of orbit 1 is 0 and F of orbit 2, you can always rescale things, is not 0, so say it's 1. All right. And so what you quickly discover, thinking of these terms with invariant functions, is that closed orbits are key. Why? What's happening is that the functions, well, they're continuous. And so an orbit is going to be identified by a function with its something as closure. So if I have something like this is a closed orbit, something like this, right? Then the function is going to be the same value here and here if it's an invariant function, right? So, okay, that's really easy. So what can we do in this case? Well, in this case, we understand it very well. We know that determinant and trace are, similarity invariant. So they're invariant functions. Let's try and use them to separate things. Okay, so, well, what we do is we just consider the map. Phi, defined to be the pair of functions, determinant, trace, is mapped from 2 by 2 matrices to your base field to the second power, of course, because there's two functions. And you can ask yourself, what is the fiber? What does the fiber look like? Well, so there's two cases. There's a general fiber, there's a special fiber. So the general, that's green for good. Right? We have lambda 1 and lambda 2 are distinct eigenvalues. All right, and the special case, so we know this is generic, right? This is the generic case. And the special case, which I'll do in red, is when they're actually the same eigenvalues. We'll call that. All right, so what happens here? Well, it's easy to see that in this case, so if you pick a point not on the diagonal, point not on the diagonal, then the fiber is going to be two-dimensional and closed. So it's a two-dimensional closed orbit. Whereas in this case, well, we know from our theory of canonical forms, which was actually done in 1870 or so, so it was not too far from when Hilbert was first doing his work. So from our theory of canonical forms, right, these are all going to be, well, this is just from the definition of eigenvalue. It's in the fiber for all t. And from our theory of canonical forms, we know that they're all similar to this, right? At least, let's see, yeah. And so now what we conclude is that because this is in the fiber, and the limit of this as t goes, yeah?
What is happening?
Oh, sorry. So, so I have a map, determinant trace, going here.
I'm just confused about that second matrix you wrote.
Lambda. Thank you. Too many little.
But I'm still, I mean, no.
Sorry.
What about t equals 0?
Yeah. So I'm taking lambda 1 equals lambda 2 equals lambda.
And that t equals 0 is not similar to that guy.
Yeah. Thank you. But the point is that this is going to give me, this is going to be an open orbit, and the t equals 0 case is going to be in the closure of that orbit. So thank you. So so the point is that exactly that that t equals 0. This orbit, well, what is this orbit? This orbit is just itself because it's a constant matrix, and so it commutes with b and b inverse, right? So this orbit is just a point, so it's closed. And this is a two-dimensional orbit. Check. Not closed. But this is, of course, in the closure of this. So you get a picture sort of like two-dimensional, and then we have a one-dimensional special point there, which is closed. Okay, so this picture, where we have some map of invariance, and we get fibers that are well-behaved, where we have, in each fiber, a unique closed orbit, turns out to be sort of the general case, as long as we pick the right enough invariance. So one thing you can check, simple exercise is so we know that phi is surjective. We know that. And so your exercise would then be to verify that determinant and trace generate the invariance in this case. All right, so what are the key remarks? So first of all, zero. The fiber over 0 has some nice structure. First of all, it's of this type, right? The eigenvalues are the same, so it's one of these special ones. And you could sort of think of it as maybe a nonlinear version of a kernel. The determinant there is the trace may be linear, but eigenvalue for the determinant is nonlinear. Nonlinear kernel is distinguished in some way. In particular, it has a nice property that you can rescale all the coordinates and still get back your space, the fiber over 0. So it's preserved as a set under rescaling of coordinates, and so we can call it a cone. Because it's a cone over 0, we'll talk about it as a null cone. Okay, the second point is, has to do with that. So we've seen that the orbit space is just a copy of C2, sort of, but it has some redundancy, right? I mean, we have this orbit, the open one, is not the same as the orbit in the closure. It's just the functions don't see the difference. So what's happening is, really the orbit space is C2, K2 with a line doubled. So but the quotient via the invariant functions is actually your plane. Okay, the third point, which I guess is my second point with numbering, is observe that y, so we use determinant and trace rather than the eigenvalues, because your first impulse, knowing your Jordan canonical form theory, is to just say use the eigenvalues. Well, that's fine, and you'll get two eigenvalues that are independent. So you're going to see two back. But again, this is the issue of elementary symmetric polynomials I mentioned before. So if you try to choose the eigenvalues, you can think of it as choosing a sort of a slice up above, but that slice will have some non-trivial group action on it, which you, strictly speaking, should quotient out by, even though it doesn't make a difference for the quotient variety. All right, third, if instead of the two-dimensional case, well, you did the higher n, well, it's very similar. I mean, of course, you're going to get the same sort of structure, but now you're going to have finitely many orbits to worry about in your special fibers. So general is still going to work as before. But the special, now you're going to have finitely many, and the invariants you're going to use are going to be the other symmetric polynomials, of course, and eigenvalues. Now you have finitely maybe greater than 2 fiber, but you always have unique closed orbit in each fiber. That is to say, these invariant functions are separating the closed orbits. All right, so what now happens is a fourth observation. What happens if instead of using C, we used some subfield, like Q? Well, maybe you have more orbits that arise, but you're still going to have this unique closed orbit phenomenon. So somehow, this is independent of arithmetic information of that sort. So this is 3, this is 4. So over Q, for instance, so set, but still, and this is again going to be something somehow general, is that when you change your base field, you extend your base field, that somehow this property of being general or special in this way is independent of that. So that somehow there is a sort of independence of the arithmetic, at least with the base field. Again, this is somehow primarily topological info, and I mean that in a sense that can be formalized nicely in terms of homotopy theories and so on. Topological. So 5. So the other thing that 19th century people would point out is determinant and trace and so on are these invariants, but these invariants, they form a basis for invariants.
You swallowed the next few words after topological. What were they?
Yeah. So the point I'm trying to make is that we're trying to do something, or not we're doing something which is going to be in some sense independent of field extensions. And that tends to be very good for certain algebrogeometric theories, like A1 homotopy. Okay, yeah, so mainly the point I'm making is this, that it's independent of the arithmetic of the base field in some way. So, or some properties are at least, which we'll get to later. So determinant and the trace form a basis of the invariants, generating set, but they have nice distinguished geometric properties. And this is what the 19th century people adored, that invariant theory somehow produced extremely nice geometric interpretations and proofs. Okay, so let me get to the next example. This was the first motivating example, linear algebra, prototype for all classification problems. Really going back, as I said, to 1870, Weierstrass and Jordan. Now, what about, and Hilbert was first working on this stuff in 1890. What about the next example? Well, there's other things you can do. I guess the diagram's still there. We have other classification problems, which we can translate into group actions by the same philosophy. So let's do things in Euclidean geometry. So instead of linear algebra, Euclidean geometry. So let's say the real plane, and you want to classify conics. So it's going to be two curves. And so if gamma is your curve, and say everything is nice and irreducible, smooth, and so on if you want, pick your parameters so that it works. All right, well, we have the group of Euclidean motions in the plane. So we can consider this up to Euclidean transformations. But what is that group of motions? It's the group of motions. Slightly more interesting. I mean, you might include reflections, you might not. And I'm probably getting the order direction wrong in the symmetric product. But it has these translations. Right, so this is the translations, and this is rotations and flips. And so this is somewhat different in character to the other one, which was a GL. We now have, wherever it went, we used GL as the group. Now we have a slightly more complicated looking group. We can still play the same game. And you can ask, what are the invariants? And what do they tell you? And so you can just list the invariants, and it turns out this will work. You can do A plus C. Let's call this an exercise. A plus C times delta to the negative 1/3. And F2 of gamma is going to be AC minus B squared times delta to the negative 2/3, where delta is the determinant of the following nice matrix: A, B, B, C, D, D, E, E, F. Okay, one can check, and one can check then that these invariants do indeed distinguish all of your conics. So you get your ellipses, hyperbolas, parabolas, appropriately characterized. And you can pick natural representatives with your equations then. Okay, so Euclidean geometry works even though this group is a little bit funnier than the other one. Again, just by taking invariants. Well, what else can you do? And this is, again, beloved by the late 19th century people. You can do projective geometry. So you might begin with looking at a hypersurface, for instance. Look at f equals 0. And then again, you pick coordinates and you quotient out by the possible projective changes of coordinates, and you expect that will tell you something interesting geometrically. So the idea is that invariants should detect properties that are independent of the coordinates of and so are geometric properties. Nice 19th century philosophy, and pushed to its furthest extent, you get Klein's Erlangen program. So, but sticking to this for the moment, I mean, so you get the first classical example of a moduli problem in algebraic geometry. So moduli of hypersurfaces comes from PGLN action on some large enough projective space where the dimension of the projective space depends on the number of coefficients defining your generic f in whatever smaller projective space you use, right? But you end up getting then an action on a projective space. And it's sort of a fact, again, an exercise, if you like, early in Griffiths and Harris, is that this notion of equivalence, at least for smooth things, this agrees with abstract isomorphism as varieties. So it really is giving us moduli in our modern sense, used for smooth things. And the other thing you can do is you can go further. I mean, why stop with just one hypersurface? You can consider many hypersurfaces. You can consider configurations. Of hypersurfaces. So now you're going to be doing hypersurfaces in a collection of little PNs. So in the simplest case, you might do P1, for instance, P1 to the 4. So there's 4 points on P1. All right, so what are the invariants? So invariants of these will give you geometric properties let's do this for a moment, of the configuration of hypersurfaces. P1 to the 4, it's just 4 points on P1, ordered as I said, and what you get as an invariant is just a cross ratio function, and so on. So the key point is that the relations among invariants are going to give you the basic theorems of projective geometry. And you can, in principle, derive all the geometric theorems of projective geometry from invariant theory. In fact, you can do much more. You can derive, in principle, all the geometric theorems of any geometry that is in some sense derivable from projective geometry, like Euclidean and affine and so on. So that is Klein's-Erlangen program. So the idea is that relations among invariants, theorems in projective geometry. Okay, remark, take subgroups before you define a group, get other geometries. So for instance, Euclidean, affine, etc. Anything derivable from projective geometry. And as I said, in its purest form, this is statement of Klein's-Erlangen, which is what Hilbert was steeped in at the time. So in fact, in his day, algebra and geometry were linked by invariant theory. They were more or less exactly the same thing. So algebraic geometry of late 19th century is invariant theory. You might say this is the sort of geometry of invariance rather than geometric invariant theory. All right, so this was the, So just to stress it one more time, you're saying methods of invariant theory give you all possible theorems in projective geometry, right? In principle. Practice, hard mess. Okay, so this was setting for Hilbert's thinking. All right, and what was Hilbert doing? Hilbert was studying basically this problem here in projective geometry of hypersurfaces and some configurations of hypersurfaces. And so he was studying, if you like, special classes of representations of SL. Okay, and what did he do with it? Well, the broad idea, and all of these examples, as I said, is to study geometry through invariants. So you want to know what the invariants are, or at least a generating a set for invariants are. And that's going to give us our notion of quotient. So that then raises a host of issues. Use a complete set of invariants to define a quotient of some sort. Well, what sort do we mean? This is what you have to discuss. And in particular, because we're using invariants, and these are continuous functions, so you're picking out closed orbits. Can't stress that enough. All right, and so the quotient, first stab at a quotient is, you might try to consider something like a categorical quotient. So in your whatever category of objects you're working in, you want to stay in that category. And so if you have, so you would want such a thing to satisfy a universal mapping property. Quite easy. If X is a G variety, then you want the quotient map phi, like that. You'd say anytime you give me a invariant map to some Z, this quotient, your universal quotient, your categorical quotient, is going to, that map will factor through the universal quotient, right? So that's the idea. But you, of course, have to be very careful with your choices of categories. It'll make a big difference what's going on with this diagram. So particularly even in algebraic geometry, give a couple examples. Really matters. So we didn't quite see it from those other examples, but here's a simple way to see. So here's a nice clean example. Take SL2 and look at the additive group represented by 1T01. And so that acts on matrices in SL2 in the obvious way. And then you deduce what the invariants for that action are, right? So it's just A plus TC, B plus TD, and then CD. So these coordinate functions are invariants. All right, well, then what's the invariant map give me? Well, the invariant map, just like for our determinant trace before, we're mapping down to a two-dimensional space. So it's going from SL2 to A2. Okay. So we're going from SL2 to A2. And what are we hitting? With the determinant trace, we hit everything for when we worked with classical matrices. But now we can't have C and D both simultaneously 0. So what that actually means is that SL2 is surjecting down onto A2 minus the origin in A2, which is very different than what happened before, as I said. All right, it's a small difference, but it could be very important. Okay, so this, as we know, is not an affine variety. It's quasi-affine, but not affine. What else can happen? So this is example 1. Example 2, I wanted to have a picture for you, but I didn't get the projector thing set up today, and I'll do it tomorrow as part of a more natural discussion. But you could treat it as an exercise then, until then. Exercise. Consider a smooth affine quadric surface, which we might call Q2. And then there exists a nice map with fibers that are A1, so exists, in fact, a GA action, such that Q2 maps surjectively down to a line, an affine line, with a doubled point. And the fiber is a group action. It's a free group action, almost theoretically free group action. So I want to have this fine. With a doubled point. Okay, so it's set theoretically free. Okay, so I mean, this is as nice an algebra geometric picture as you can get, and yet if we consider just our standard invariant functions, we're not going to see this, right? So the invariants won't detect that behavior. Yeah, there's our categorical quotient issue. We want to be careful what we choose, but for the moment, let's just choose the category of affine varieties. That's a natural thing, given what we've been considering. Well, ideal is something more complicated. And things can get much worse. It's really easy to give examples that are algebraic spaces but not schemes and so on, but the action is as nice as can be. It's nice and free, even in a scheme theoretic sense. So you do have to be careful. But let's do it for, as I say, affine varieties. So the above idea, following our above idea with invariants, list some invariants, call them F1 through Fs, and define your map then, which is hopefully going to give you a quotient, to simply be that list of invariants. And so it gives you a map from your variety X, I guess I called it, to affine space over your base field, S copies of them. Right? So the first coordinate is F1, last coordinate is Fs, and then you consider the image and take its closure. Well, that's an affine variety. And it's an affine variety whose coordinate ring of functions is just given by these invariants. All right, so we'd like to be able to say that this is the categorical quotient in the category of affine varieties. But there's an issue. Well, what's the issue? The problem is that, for one thing, this is only can be made. You can only do something along those lines that's canonical if you want to stay with affine varieties. Canonical if the invariants are finitely generated, right? If the so this was the big issue at the time in Hilbert's day. And not only did you want finite generation, but ideally you would have a description of the invariants, that is to say the generators and the relations of the invariant subring. That was seen as the main goal of invariant theory, to get that as explicit as possible, because in part it tells you all possible theorems in geometry, right? So, in principle, whatever that really means in practice. So in 1890, Hilbert proved finite generation for his class of actions. So these SLNs, basically, linear representations of SLN. And he does this by first, to prove this, in this paper he proves his famous basis theorem. So this is standard commutative algebra, which everyone has seen in basic course in graduate school, say. Although the application to the finite generation of invariants does require a bit more work, of course. But the goal of the Hilbert basis theorem wasn't the basis theorem, it was this. All right, so then he asks, so this is sort of an intriguing problem. It was unfortunately criticized at the time by Gordon, we'll get to that in a moment. But the general problem he liked enough to formulate as one of his famous problems. So Hilbert's 14th problem is basically the statement that, let's make it more precise, it asks whether there exists invariant, so a group action, say a linear representation of a algebraic, say linear algebraic group G, such that the ring of invariants is not finitely generated. He thought they all would be. It was just a matter of being clever enough. At least that's historian's impression. But let's continue. Others, in particular Nagata, many decades later, realized that Hilbert's technique applied to a very large class of groups called reductive groups. And showed that you get finite generation for all reductive groups, which is basically just adapting Hilbert. So what's a reductive group? We'll discuss in more detail tomorrow all the properties surrounding it, but the simple point is just it's the maximal connected solvable normal subgroup is a torus. So really we're talking about things built from finite groups, semi-simple groups, and tori. Okay, and this theorem, this conjecture rather, the problem, although it feels very old school style, is still quite relevant today. Appears all the time in algebraic geometry, some form or other. It's usually hidden. Whoops. So let's say that, first to finish that line of discussion, yeah. So we'll open a quick parentheses, then get back to the main storyline in just a minute. So the theorem of Nagata is that there exist counterexamples. So is that 2 Hilbert's 14th. And then there's a theorem of Popov building off of that, which says that if G is not reductive, then you can always find a counterexample for that G. Strictly speaking, we'll do this with affine varieties instead of linear representations, but whatever. It's not a big difference. Okay, so then Zariski had a nice generalized version of Hilbert's 14th, which brings it more into the modern day. So we'll say that if R is an affine ring over K, and L prime is a field with K and L prime and L, which is the field of fractions of R, all right, then when is R intersect L prime an affine ring? You may want to insist on normal as well, but it turns out not to matter so much for the ultimate formulation, I'd say. This can be thought of then, so Zariski and Mumford pushed the interpretation of applying this problem to geometry by considering, if you have D as a divisor on some projective X, then you can look at the following. You can look at XD is equal to direct sum of the space of sections of X, the line bundle associated to D, so it's a Cartier divisor, tensor M for M equals 0. And you ask when this is finitely generated, and lots of variants on that. And then you can go full circle and say that this conjecture actually is a question about invariance again, because it was a theorem, not too difficult to prove. And I guess at some form it may have been known to Nagata. The first time I saw it in print was due to Winkleman, I guess 2004, 2005, which is that you can always interpret this problem in terms of invariance, at least when things are normal, and it's relatively easy to generalize this if you leave the context of groups and do unipotent vector bundle torsors and allow those, so somehow families of group actions, to even dump for normality assumption. So I won't bother writing it down. I guess it's 2004, is that this is equivalent to the original 14th for non-reductive, in the sense that you can find given this problem, you can always find a X and a G such that X affine such that they are not finitely generated. Infinitely, this is not finitely generated. In fact, the rings will agree. That's all right. So it's going to run a little bit low on time. I of course wanted to say more. Okay, so closing that parentheses. We'll get back to later. So Hilbert's argument was criticized by his referee for the paper, Gordon at the time. He sent it to mathematician Allen, and Gordon wanted it rejected. His critique famously was that because it's not constructive, he said this is not mathematics, this is theology. And Klein, who was the editor of the journal, used his editorial discretion to overrule his referee and had it published anyway without any changes. But Hilbert was either distraught or inspired, depending on how you view this, by this critique. And with Klein's encouragement, he worked hard for a number of years, 3 more years, on a fix to try and make this constructive. So in 1893, came out with his second paper, which is one of the core papers in the history of algebraic geometry, all to sort of solve this problem. So the point was that the crude idea is that we have these generators F1 through Fs, so we can look at the ideal generated by F1 through Fs and an associated geometric object, namely the variety associated to this, or the null cone. Which we discussed before, right? Just the zero set. So his rough hope would have been, so the naive hope, which of course is not true, would be that if you can find another way to get at, to describe the null cone, then you can work backwards to compute this ideal and its generators. So the basis, F1, etc. Now, of course, this doesn't quite work. When why doesn't it quite work? It's because you're really geometrically working with the radical of the ideal. And to understand this properly, Hilbert proved in this paper his Nullstellensatz. Okay, so what he discovered is that he had enough information to compute not the invariance, but of course this radical ideal, and we'll explain how in a more high-tech way tomorrow. But the point is that he was able to compute a so-called system of parameters. Right? So in essence, he proved a graded version of Noether's normalization theorem in the same paper. So described, so sufficient to get a system of parameters. So in particular, you know the dimension. And in fact, you get a finite map down to an affine space with the right dimension. The dimension. But we need, so this is, he proved another normalization. But what we need is a degree bound on that map. So he needs degree bound. And there he failed. He wasn't able to do it even for his simple examples. He could only give degree bounds in the systems of parameters. Nonetheless, this paper was accepted. It has some nice results in it. And of course, became the foundation of modern algebraic geometry. And Gordon, well, I'll say that in just one more second. So I'll go over just a couple minutes. So what's the idea? His core idea to describe the geometry of the null cone to get at invariance was a very good one. And this is what we would really call the beginnings of geometric invariant theory. So geometric invariant theory a la Hilbert. And to be honest, it pretty much is geometric invariant theory. There's not too much more to it. It's just a matter of being very careful. So the point, though, is to finish the story does have an end. It doesn't end sadly with this failure on the part of Hilbert, but rather over the years, people began improving the degree bounds, and it turned out that there's a number of ways to try and do that, and to prove it for reductive things. As I said, you have finite connected semi-simple tori, and if you prove degree bounds separately for each of these cases, you can put it together and get degree bounds for reductive groups. And lots of people did this. Noether, at least with some characteristic constraints in your field, prove the degree bound. Order of the group is bounds above the degree of the generators. There exist such generators, rather, bounded in that way. Popov dealt with this in 81. And then tori were dealt with in two stages by Kempf in the 80s, and then Willow in 1993. And so this then implies there exists an algorithm for computing the generators and ultimately relations of invariance of reductive group actions. Okay, but it was better than that. It turned out a few years later in Dirksen's thesis that if you just reformulate these original questions in terms of the modern language of algebraic geometry, and of course we discussed group actions in this way, then actually Hilbert's original idea was basically correct if you just have the tool of Grosvenor bases. So quickly, Dirksen, it's kind of amazingly simple. And what he showed is that if you consider the modern language, as I said, so we have a group action, let me put it where everyone can see it. I mean, it's just standard categorical. Take G cross X going to X. G is a reductive group. X is, say, an affine variety, or you might as well just do things for linear representations. That turns out to suffice. So let X be a linear representation. Consider this. Goes to X cross X, group action. And let's call that psi. Then the image of psi will take to be something called B. Then B bar is the Zariski closure. And we'll say that B bar, Zariski theorem, is that on the geometric side, B bar, oh, I should say what this is. This is so G comma X is sent to X, right? Is equal to the null cone as schemes. And ideal theoretically, you actually recover the ideal of invariance in this way. So ideal theoretically, we have our ideal B plus this will be associated with what's called the coordinates y1 through yn for the first x. And for the second x, we'll use x1 through xn, or vice versa, is equal to the ideal, which is the ideal generated by the invariance. And then with some simple commutative algebra, which is just an evolution of Hilbert's basis theorem. So really, it also goes back to Hilbert. His first paper. You're done, and you get your theorem then that you can compute. Obviously, I'm skipping steps here, but the idea is, or at least over a characteristic zero field, and G reductive, there exists a set algorithm to compute the invariance, and I'll say in the spirit of Hilbert. So his crucial idea for us is going to study the geometry of the null cone. With just a little bit of modification, it turned out to solve the original problem he was facing at the time. And I will end then today's lecture on the following note from Gordon. To remark, so ultimately, about 100 years later, his vision was fulfilled completely. And at the time, once this had become more widely accepted, Gordon, once Hilbert's ideas, of course, in algebraic geometry became more widely accepted, he said, I've convinced myself that even the theology has its merits. So hopefully the next 3 lectures will be more than theology, but this is the crucial point. Thank you.
Can I just, if we have tea, can I make an announcement, please? If you want to use the library computers, you'll find that the password on the piece of paper given in your packs is incorrect. I won't go into why that is. It's a technical reason. I don't understand it. But you do need to get a new piece of paper from the reception desk, which you could conveniently do now if you wanted to use the library computers this evening. It doesn't affect any wireless.